So welcome everybody to our 7th seminar in the Algebra, Particles, and Quantum Theory seminar series. And I'm pleased to introduce you tonight's speaker, Andreas Trautner. Andreas is currently a postdoc at the Max Planck Institute for Nuclear Physics in Heidelberg. Andreas completed his PhD at TUM in Munich and next went on to complete a postdoc in Bonn and now is has a longer-term fellowship at the Max Planck Institute in Heidelberg. Andreas demonstrates a highly unusual breadth of expertise from experiment and phenomenology on one end of the spectrum, all the way to formal aspects of QFD, mathematical physics, and string theory. Tonight, he will be telling us about the implications of outer automorphisms of symmetries in QFT, what he calls symmetries of symmetries in particle physics. Now, before we begin, I'd like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, of course, it's not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. Okay, so Andreas, anytime you're ready.
Thanks so much for the invitation and this nice introduction. So I just, heads up, I cannot see raised hands. So if there's any question, I mean, just speak up, or maybe Cohl will see you, but
I'll take care of it.
Just speak up, yeah, cool. Yeah. This has, I mean, we just discussed it. This is work which I started during my PhD and continued after that. And so it's based on a series of papers and with a bunch of collaborators that you can see here. Okay, so to start this off, let me just give you a little bit of a picture that you should have in mind. What we're after, what we want to discuss today is so first let's get a picture for symmetry. So if you think about a symmetry, then and the way I think about it is you always have some object, some representation that the symmetry acts on. And so for example, in the case, imagine you have a square and the symmetry of the square is d4. And it consists of, for example, rotations by 90 degrees, which leave the square invariant, or you can have reflections on, say, two different axes, which also leave the square invariant. And so this is how you can define the symmetry group D4 of the square. Now, if you look at the square, I mean, it has edges and it has corners or vertices. And so if you look at the action of for example, this reflection, you notice that you identify, so two of the corners are mapped on themselves, while as two corners are mapped onto the other corner. And so you would, on this transformation, kind of map this corner to the other corner. So two corners are left invariant, while two corners are mapped to each other. Whereas if you look at the edges, you see the four edges under this transformation, actually all of the edges would transform non-trivially. So you map this edge to this edge, the red ones, and the green edge to the other green edge. If you consider the other reflection, exactly the opposite thing happens, namely two of the edges are left invariant by themselves, while as you actually have the four corners are pairwise identified as were the edges before. Okay, so if you think of doing the following operation, I mean, you have the corners and edges, and I just come up with another square where I identify a corner with an edge and an edge with a corner. I could draw it like this. So basically this edge here corresponds to the corner, and this corner here corresponds to this edge, and so on. Now, if I consider again the action of these two reflections, now the reflection which for the one square say, for example, identifies two corners, but leaves two corners invariant, is for the other square exactly the operation which leaves none of the corners invariant, but identifies the two edges. So, of course, both of these squares are representations of D4. So you may think it's probably pretty much the same representation, which is not true. If you consider both of them relatively to each other, they are different representation of the same group. And so while as the group will never ever turn one of these squares into the other, there is a transformation which is outside of the group, which is an automorphism of D4, which is Z2 automorphism. And what it does, it maps this square to the other square. And so this is very simple picture of how you see the action of of an automorphism on a representation of symmetries. Now this, of course, is a pretty simple example, so it continues to more complicated and interesting things. I mean, just one example for geometric objects is where you have, for example, the same thing that you have automorphisms. I mean, you don't always have to identify the same things, and it's just identifying representation. So, for example, you have the icosahedron, which is identified under an automorphism with the great icosahedron, or this thing, which is called the small stellated dodecahedron, which is mapped to the great dodecahedron. But in principle, I mean, it's a very general thing, these automorphisms and the action on representations. And so this is what this is about today. And the object we will be discussing is, of course, more physical objects than these solids. Okay, so what I will do next is some short introduction to automorphisms. And I'm sorry if there's a very mathematical audience and you all know about this, then in case you do that, then just stay tuned and listen to this very physical picture probably of how I understand these transformations. Then I want to discuss that the CP transformation is actually a special automorphism, and I will discuss it in detail. And then we go to discuss some automorphisms beyond CP transformations. And then I will discuss this based on an explicit example, which will be a 3-Higgs doublet model. Okay, so what is an automorphism in general? So I was disappointed when I opened my favorite group theory books for the first time and looked up this definition, because it's kind of a negative definition in the sense that you define the automorphisms as all which are not inner. So you first have to, find automorphisms, then find the inner automorphisms, and then you can find the outer automorphisms. This is of course unpleasant, but in the end, I mean, it's just this thing. I mean, you have the automorphism group of an object, in this case a group, and you know the inner automorphisms, and you mod them out, and you end up with the outer automorphism group, which is not the subgroup of the automorphism group, but a coset of automorphisms. So more concrete, let me give you just one example. Maybe it's too simple for you, but this will save the purpose of introducing this stuff more formally. So it's not very uncommon, that groups have automorphisms. So this is, Z3 is very, very small and pretty trivial. I mean, next to non-trivial group, and this already has non-trivial automorphisms, and it's a general property of these groups. So if you think of Z3 as being generated by one element, then I have just one relation which generates this group. Is A cubed is the identity. So I can write down a list of elements of this group C3, just the identity A and A square. And A cube, of course, would be the identity. So this here is the character table of the group. And what the automorphism transformation does is it just maps A to A square and maps A square to A. So it just as a permutation in this list of group elements that is consistent with the multiplication rules of the group. So the way how you can think of this is as a conjugation map, even though I warn you, this mathematically not entirely correct and sound, but nevertheless, it doesn't hurt, because formally you wouldn't have a multiplication defined between U and A, because U is not part of the group. And the way how it acts is, if you permute A and A square, you can equivalently see that as a permutation of the representations of C3. And in this way, you understand how you can find and how you can view this as a transformation among the representations. So the picture you should have in mind is, if you have a group, there may be an automorphism group of elements which live outside the group but take elements from the group to inside the group.
Can I just ask a quick question? Can you always describe an outer automorphism via some form like this UAU -1?
If you think about explicit representations, I would say yes. And since I would say yes. Yeah. I don't know of any single example where this wouldn't work. So in abstract sense, this automorphism is a reshuffling of symmetry elements, not an arbitrary reshuffling. The group itself tells you which reshufflings are fine with the group and which ones are not, and the ones which are fine are the automorphisms. So in words, this is why I call it a symmetry of the symmetry, because it's if you view the group itself as the object, the automorphism would be the symmetries of this object, and namely the non-trivial symmetries of this object, because the trivial ones are kind of inner automorphisms, and the non-trivial symmetries, which do not live in the group, are outer automorphisms, so symmetries of symmetries. Now, in a concrete sense, if you want to use this for physics, you have to think about representations. And what it does is these automorphisms provide a one-to-one mapping of representations. And then if you go to these explicit representations, they are represented by matrices. And what you have to do in order to find the transformation matrix of an outer automorphism, namely think of it as the representation matrix of the outer automorphism, and then you can define matrix multiplication as the multiplication, which then gives sense to this equation. And then what you come up with this, what we call the consistency condition. What you have here is a representation. I mean, say the one that you start with, and you have U of G, which is the automorphism on the group elements. And then you have on the left-hand side here the representation what you end up with, and these matrices which define the transformation behavior on the representation under the outer automorphism. So this here is written very general. So you have one representation R mapping to one representation R prime with this automorphism U, and you can actually show that this is a one-to-one thing. I mean, if you can find solutions to this equation, so valid use, then there is an according. I mean, then you find this abstract transformation of the group elements, and vice versa. If you do not find such a solution to this equation, then there's also not such an automorphism on the group. So now one special case that I will discuss in length is if representation R is some, I mean, you start with R and you map to R prime, but if R prime is the complex conjugate representation of R, then this we will see very general. This is a very important transformation for physics because it will correspond to a CP transformation. Okay, so if you have a group, the group itself already tells you what automorphisms it has, and so it's useful. Or I mean, you may wonder how you do know about these automorphisms without doing always very explicit computations. And so for continuous groups, or more specific, simple Lie algebra, simple Lie groups, the automorphism of the corresponding group is given by the symmetries of the thinking diagram of the algebra. And in this case, already it's very special situation for these simple Lie algebras, because the Lie diagrams, the thinking diagrams have either Z2 symmetry or none, or there's one special case, SO8, which has S3 symmetry. And whenever the Lie algebra has the thinking diagram has Z2 symmetry, it's a group which has complex representations, and in this case, the automorphism will act as a complex conjugation on these representations. If the group does not have a Z2 automorphism, it also has only real representations. Therefore, it also doesn't have an automorphism. Then again, this very non-trivial example, the only one is SO8, where in this case you would have 3 8-dimensional representations, for example, and the automorphism would act as S3 permutation of all 6 permutations of these 3 representations. So for these things, it's easy, and the automorphism groups are small. Now, if you think about discrete groups, it's of course a very nice playground for these kind of things. So I talked about the group Z3. Now, let me give you a more non-trivial example, which is the group delta 54, which will appear throughout the talk as an example. Don't mind the complicated character table here. What is important is that you look at a list of representations here. So delta 54 has 4 doublets, and it has a bunch of triplets, which are complex representations. The doublets are real. So now in this case, or in general for these finite groups, you find situations where the automorphism group actually, they become quite large. So for example, for delta 27, which is a group with 27 elements, the automorphism group is bigger than the group itself. Okay, so this is nothing unusual can happen. For delta 54, we have the automorphism group is S4, which is permutation of 4 elements. And how it acts, for example, on these 4 doublets is exactly as you would expect, as all possible permutations of these 4 doublets. And so if you want to find this for a specific group, we can do this by hand to a certain extent, but then of course you can also use some help with software tools, and the one I use here is SCAP. Okay, so what does it have to do with physics? So if you think about the standard model, which I write here just given by the gauge group SU3 cross SU2 cross U1, and the Lorentz group for spacetime, and a CP transformation, and I just state this and maybe explain a little bit more detail on the next slides, corresponds to simultaneous automorphism transformation for all of these groups. And namely, it's a very special automorphism transformation, the one which complex conjugates all representations. Okay, and by all, I mean all, which means each of these, I mean SU2, SU3, U1, but also the Lorentz group, which in this case maps, it acts on the spinors. So the physical meaning of this transformation comes in when you think about what happens if you would have this transformation and you apply it to the standard model, and it would be conserved. If you would conserve such a transformation, it tells you that all CP, I mean, this is why we call it CP transformation, all CP odd quantities, like for example the SU3 theta angle, and also the phase of the CKM matrix, they are forced to be zero. So this tells you that experiment tells you that since these quantities, at least the CKM phase, is non-zero, that transformation like this is not conserved in nature. And actually, violating such a transformation is also a necessary requirement for baryogenesis, or like explaining the question about the baryon asymmetry of the universe. But I mean, we understand that the universe is baryon asymmetric, but we cannot explain the size of the asymmetry. And so thinking about these transformations and violation of this transformation may be a certain interest for phenomenology and for nature. So for example, there's one of these questions: why is this CP violating? So sorry, I wrote the delta CP violating here, and this delta CKM is the same thing. Why this quantity is large and non-zero? So CP is violated, whereas the theta angle is so small that, so we noticed from experiment that it looks like CP is halfway conserved in one sector and broken in another, which we don't understand either. So there's another question why it's interesting to think about this, the structure behind these transformations and the implications. So in a little bit more detail, so why do I say this is complex conjugation automorphism? So I don't want to go into all the details here. I just want to show that you can actually do the sound math also behind this thing. And if you think of a theory like so this would be just, for example, a QCD theory where you have fermions and you have the gauge fields, and the fermions would transform in a certain representation of this SUN, say, Lie algebra. And so you can think of what is the most possible general CP transformation. Here CP is, you should think of the most general complex conjugation transformation in this theory. And I mean, forget about all these complicated things here. The most important thing is, and this is my physicist way of thinking about these things, but if I have an object, say a spinor or this real gauge field here, or the field strength of the gauge field, whenever I have a field that has an index, each index has to transform with a matrix. So here, I mean, for example, P mu is the parity transformation, it acts on an index, and RAB is the automorphism, I mean, transforming in the gauge group, and it acts on an index of the gauge field. So this is the same thing as I said before. So this matrix R here and the matrix P here are the same thing as I called U before. It's the representation of the automorphism acting on an object. Okay, so not surprisingly, I mean, if you say I want this transformation to be a symmetry of this Lagrangian density, then you find it can be conserved symmetry of the action just from looking at the kinetics terms, if and only if these three equations hold, And all three of these equations are what I would call a consistency equation. They all follow the form that I've shown you in general before. It will always be like, say, like two U matrices or U and U inverse on the left-hand side, and a transformation on the group, like an automorphism acting on the group on the right-hand side. And in fact, this is why I'm saying it's complex conjugation, even though here you do parity transformation on Lorentz group and complex conjugation on, say, the SU engaged group. In fact, it's a complex conjugation on all representations. So also the Lorentz group representations here are complex conjugated. So let me elaborate this a little bit more on the next slide. I will come to that shortly. So if I think of this, I mean, in the standard model, it's kind of, I mean, straightforward, okay? But I also want to discuss more general theories. And so if I want to discuss CP violation in more general theories, I have to be very careful about what I call CP transformation and what not. I mean, I already told you that I will look at this because in the standard model it's given as complex conjugation. It should also, you know, go to theories beyond that. And so to be more careful about this, what you have typically is you have a physical observable, like in this case would be an asymmetry where you have initial state and final state and some conjugate initial states and conjugated final state, and you wonder about the difference in amplitudes or normalized difference of these amplitudes. Then you can show that, I mean, taking again the example of the standard model, that this typically is related to, so this is a one-to-one relation here, to basis invariant objects in the space of couplings of the series. So here I have, for example, again, for the standard model, you have mass matrices of up and down quarks. And so they live, you know, in what I would call flavor space. So they have indices in this space, and I have to contract them in a way that I get rid of all these indices, which makes it a flavor basis invariant. And I have to do it in such a way that the object, this invariant object has an imaginary part. And in fact, turns out for the standard model, this is the only independent quantity which fulfills this condition. So in order to have CP conservation, say if I define these guys I and F as the, in this case, CP conjugates of the initial and final states, I want to have this asymmetry to be zero, and there's a one-to-one relation which entails me also this what is called the R-Cook invariant has to be zero as well. Now, in order to vary this by a symmetry, okay, by a transformation, by an active transformation, I need a map which tells me if this map is a symmetry of the theory, then J has to be zero. And the only way how I can do this is I have to map here the mass matrices to the complex conjugate. Now, of course, I don't want to have an active transformation on my couplings, but what I can do instead is I can equivalently do an active transformation on the fields. So this is a schematic view here. So I have a real Lagrangian density, which has couplings and operators. And what I do, instead of mapping the couplings to the complex conjugates, I can map the operators and containing fields to the complex conjugates. Now the transformation that does that, as I said before, if I want to map the operator to a Hermitian conjugate, I have to do complex conjugation. And so what the most general CP transformation does, it maps the fields to the complex conjugates and then ensures that quantities like the R-Cook invariants, which have imaginary parts, have to be zero. So now, one more thing is, I already said it a little bit before, but there is a common, say, I would say misconception or a little bit of a historical misnomer that people think of, if I call it CP transformation, it's something less fundamental than P or C transformation. But it's actually the opposite is the case. The CP transformation is much more fundamental than P or C transformation for the following reason. Namely, imagine I have a theory which has just a single Y spin-off. And this is the most, most basic non-scalar theory that I can write down for Lorentz group. If I just have a single Y fermion, the P or C transformation make no sense because I don't have a guy that I want to map to. While a CP transformation in this way is just, this is standard CP transformation, acts actually at a complex conjugation of this guy, which is already there. So I can always wonder about this transformation. It's always, both of these guys are independent degrees of freedom of my theory. And so I can always wonder about the CP transformation, which is just complex conjugation. While it's talking about P or C transformation, I really have to have a model which contains other guys, which may not be there. They are not necessary to have a consistent theory. And turns out, actually, I mean, the standard model is what is called a chiral theory. So it is of this nature. It just has chiral fermions, and P or C are not symmetries, are even not transformation. I mean, I can wonder about them, but they are explicitly and maximally broken in the sense that I take scissors and cut out this part. I don't need it. So extrapolating from the standard model to BSM, I just give this what I call definition of CP in words, and you already guess it. It's a special automorphism. I mean, SAA because there can be multiple of these guys. But it's a special automorphism which maps all present representations of all symmetries to the complex conjugates. And this transformation is consistent with what we do all the time. And it's the only generalization of this concept that makes sense. Now, why it makes sense is because it warrants physical CP conservation, as I tried to explain on the last slide. So if such a transformation is conserved, there will not be a symmetry between matter and antimatter. So it must be broken in realistic theories. Okay. With this definition, it's so general that this CP transformation, as I said, it doesn't have to be unique. There could be 2, 3, infinitely many of these transformations. One of them is enough to conserve matter and antimatter symmetry. All of them need to be broken by observation. Okay, this transformation doesn't have to be of order 2. A lot of people because they're used to it, assume this transformation, if applied twice, should be the identity. It's absolutely not necessary. And it's also in general not guaranteed to exist for a given symmetry. I mean, the standard model has the feature that for SUN, I can show in general that these transformations exist. For the Lorentz group, it's a bit more complicated. I have to show it manually. But as you will see next, there are symmetry groups for which complex conjugation is not a valid transformation. And
can I ask quickly about that last one of those points? So if it's not order 2, how is it a complex conjugate? So I would have expected that a complex conjugate is part of the definition is that it's an involution.
So I give you a very simple example. I should have said this before, I guess. But so since the automorphisms, for example, I mean, automorphisms are cosets of automorphisms. Okay, so I can always amend this transformation by an inner automorphism. Now imagine I pick an inner automorphism which is not order 2, but say order 3 or 4, 5, 6 or whatever. So it doesn't close after I apply it twice. It doesn't go to the identity. Then this transformation would, it maps. I mean, upon applying it once, it creates non-trivial permutation. Upon applying it twice, it generates non-trivial permutation still. So it will not be order 2. So, the square of a complex conjugation, of course, will not be complex conjugation. The complex conjugation will undo itself, but there may still be a remainder. And this remainder will not act as complex conjugation, but it will act as a linear symmetry.
Okay.
Is this clearer?
So you would somehow map it back to the same space, but it would take more than. Okay, so after twice,
if I be very explicit, if I apply it twice, let me use something. If I apply it twice, so the first time I apply it, I would map, say, a field phi to u times phi star.
Right.
If I apply it twice, I would map it to u star. I would map phi would be mapped to u star phi, and this object doesn't have to be the identity.
I see.
This U is unitary, but this doesn't, it's not, it could be non-trivial object. And then this means it acts as a linear symmetry on the theory. And this can happen. It's quite, I mean, there are groups actually, we find, I can show you examples of groups which allow for CP transformation, but only such which are of order, say, 4 and higher. Okay. And I will show you groups which do not allow for any of this transformation at all. All right.
Okay, thanks.
So, and this will lead me to this classification of groups, where in general, I would say there are 2 types, and each of them has subtypes. So the way about how I think about these groups, because I want to use them for physics, is I have a list of representations. So I have a group has a representation, I put them in a list, and in general, the automorphism will act as a permutation of representations in this list. It's a one-to-one. So then a criterion by which I classify the groups is just a simple question: is there an automorphism transformation which maps all representations, all irreducible representations, simultaneously to their complex conjugates? If there's such a transformation, I call the group type 2. If there's none such transformation, I call the group type 1. And in general, this tells me whether a CP transformation is possible or not on a given group. So this is a very clear mathematical notion that if you're interested, you should look at this paper from 2014. I will not walk you through all the details. I'm just telling you that this automorphism, this complex conjugation automorphism, in general, is called Bickerstaff-Damus automorphism, and it's a class inverting involuntary automorphism if it's order 2, but it definitely needs to be class inverting in the sense that it maps elements to the conjugacy class of their inverse elements. So in case there is such a class inverting automorphism, you can use this to define complex conjugation transformation of the group, so you end up in the type 2 category. If there's no such automorphism, you end up in the category of type 1, where you do not have complex conjugation automorphisms. In general, this is also very closely, but not one-to-one, tied to the complexity or necessary complexity of Clebsch-Gordon coefficients. So these type 1 groups, there's no basis in which the Clebsch-Gordon coefficients of this group are real. Okay, it's not said that these type 2 groups, there are also some of these type 2 groups which have necessarily complex Clebsch-Gordon coefficients, but they are such that I can still have complex conjugation in the group. And this is the difference between type 2a, where you can think of type 2a as basically being SUN groups, or groups which are somehow have the ability of that you can find a basis where all the Clebsch-Gordon coefficients are real, and type 2b groups are, and this is a category where you have the situations that CP transformation may be forced to be of order higher than 2. But if you eventually go to order 4 or 6 or 8, you will find automorphisms which allow you to define this complex conjugation map. And there's a simple, I mean, you don't have to work this out all by hand. There's this thing which is called the Frobenius-Schur indicator that you usually use to find whether representation is real, pseudo-real, or complex. And that's what is called a twisted Frobenius-Schur indicator, where you just, you use the Frobenius-Schur indicator and twist it with the action of the automorphism. Then you just have to, you can run this through a computer and find, classify the groups according, at least finite groups according to these types. So do CP transformation exist for all symmetries? General answer is no. For example, so you have discrete groups of type 1, and this is starting from the smallest group which has this feature. It's just a list of small groups which have this feature. It's not a very uncommon property. For example, all non-abelian groups of odd order, which means odd number of elements, have this feature. Doesn't have to be an odd number of elements. This is 21 is odd, 27 is odd, but the smallest group has even number of elements. Still, it's of type 1. It doesn't like complex conjugation. So these symmetry groups are inconsistent with the transformation that maps all representations simultaneously to the complex conjugate. This doesn't mean I can, see, if I have a complex representation in this group, I can map it, of course, to its complex conjugate, and I can try whether the group likes it. I may find such a transformation, but I'm saying for all representations simultaneously. Okay, this is very important feature. And this tells me immediately that I can build a theory in which CP is violated as a consequence of requiring any of these symmetries. I just have to take the symmetry, just have to take what I call a sufficient number of irreducible representations. Namely, I have to take at least a bunch of them such that this transformation becomes inconsistent due to the structure of the group. And then I have a model in which I have CP violating the complex Clebsch-Gordon coefficients of this group will enter my amplitudes, will enter the probabilities in such a way that I have meta-anti-meta violation. In this case, the corresponding CP violating phases are calculable and quantized. They are fixed by the symmetry. Okay? As I said, they originate from the Clebsch-Gordon coefficients, and this has been given a name which is confusing because other things are named the same way. Then on the contrary, as I said before, there are these semi-simply groups or simply groups on the combination, which are all of type 2. So this is like for the standard model, yeah, there always exists automorphism which maps all representations simultaneously to the complex conjugate, in which case, now you may think, oh, the standard model, it violates CP, what is going on? I mean, of course, if you have a situation that the group allows for such a transformation, doesn't mean it has to be conserved in nature. It just tells you that this transformation is allowed in principle, and then you have to do an experiment to find out whether it's conserved or not. But it immediately tells you that in this case, there's no way to predict the CP violating phase. You would have to measure it. Whereas in the other case with type 1 group, you can predict the size of these phases. So let me give you an example, and I again use this delta 54. So as I said, I mean, delta 50, okay, I didn't say that before, but delta 54 is a group of type 1. Okay, so it has this automorphism group S4, which, as I told you before, acts as all permutations of the doublet representations. And it acts, some of these, I mean, 24 elements of S4, actually 12 of them, would act as complex conjugation on the triplets. The other 12 would not. Okay. However, you can, I mean, what you find is, and this makes a group type 1, is you do not find a single automorphism in this group, which maps all representation of the group simultaneously to their complex conjugates. Okay, and actually the first time this happens, so I told you before, you have to get a sufficient number of representations of this group in to see this thing happening. Okay, and so in this case, you need actually more than 2 of the doublet states. So you need at least 3 doublets. You will shortly see why, to get this, I mean, unfold the whole power of this group in terms of CP violation. So if you, for example, would consider a model which has triplets and doublets, and it has interaction between the triplets and doublets, and if I would write down my potential of the theory, of course, I would have, I mean, delta 54 symmetry means I have to contract all the irreducible representations, and I find some coupling tensors, which are, you know, the structure of them is dictated by delta 54 symmetry. Now, in this case, you should think of this maybe as U-cover coupling. So this could be, imagine 3-1 would be a fermion, the 3-1 bar would be another fermion, and this phi guy could be a scalar. But you can also, I mean, this does not depend on this property. It could all be all scalars. Now, what happens in such a theory is, I mean, in order to see the CP violation, I could go ahead and compute all kinds of possible asymmetries and amplitudes, and this would all be very tedious and complicated. And so a much faster way of pinning down the fact that CP is violated and pinning down the fact that it's violated by a calculable phase, I could spare a lot of work by using what we also use in the standard model and just compute a CP odd basis invariant, like the R-squared invariant. So how I do this is I have my coupling tensors here. They have indices in the space of these doublets. They have indices in the space of each of these triplets. And I have to find a contraction of these coupling tensors, which has no indices, which means an invariant. And actually, I mean, in order to find CP violating quantities, I want to find a contraction of these coupling tensors, which have a non-vanishing imaginary part. And now if I go ahead and try to do this, I find that the lowest order invariant, which has a non-trivial imaginary part, comes at 4 loops. So you have some more or less complicated contraction of such tensors, but you find that it needs to contain at least 3 doublets, which is kind of confirming this, you know, what you know from the group theory, that you can only find, I mean, that you can only not find, that you can find no CP transformation only starting from at least 3 doublets. So I write this in a diagrammatic way, in the sense that, you know, each line is a contraction of indices, and each of these vertices here is one of these coupling tensors. And so you see all 2-1, 2-3, and 2-4, I mean, in this case, are involved, and a bunch of triplets are involved. And if I, you know, just contract the tensors according to this recipe, I can find this invariant. It has, depending on the absolute value of some of these couplings, but most importantly, it has an imaginary part which is fixed by the symmetry. There's no freedom, no free coupling, and there's this imaginary part. And the good thing is, I mean, if I have this invariant and I want to know an explicit physical process in this model, I can just take cuts of this invariant and find the according physical process. So I don't know if you see this very small, slight, faint dotted line here. But if I cut, for example, I cut this invariant along this line, I find, I mean, it just breaks up into 2 diagrams, which is, if you think of this guy as a heavy scalar, and the fermions as lightish, and the other scalars also is lighter than this heavy fermion, the heavy scalar. This would give you, say, 3-body decays of the scalar, these two diagrams. And these would be the diagrams that you, if you do the explicit computation of an amplitude, these would be the two diagrams that need to interfere to create a CP odd observable, which then would be proportional to this invariant. So it's basically kind of going backwards through this computation. If you let a student do it, the student would come up with this and eventually find the structure of the amplitude would be proportional to the invariant, and then find that it's fixed, but we go the other way around. Okay, just to state it, I mean, this example is also realized in a what we call semi-realistic model. So if you go from 10-dimensional string theory, you compactify 6 dimensions, you end up at 4 dimensions, you can find this delta 54 as a flavor symmetry in very special cases, and you find that all the representations are there. And so this would, and also, I mean, this reproduces the standard model at low energies. In this case, you find that there is CP violation with this calculable phases. Okay, so this is for the relation of automorphisms and CP. Now let's go and take the more general route to discuss more general automorphisms, not only the complex conjugation. So just to be very abstract here, in general, you have so as the way how I define my theory is I pick a symmetry, I pick representation content, and then I have a symmetry representation content. I can worry about automorphisms. So in general, automorphism would be a mapping of representation 1 or I to representation 2 or j. And in general, for a model, if I write it down, if I define it, I have 2 logical possibilities, namely that I defined the model based on representations Ri, right? And now I look at the automorphisms and I find that they would map Ri to Rj. So one possibility is that Ri and Rj are both included in the model, like it would be for representation and the complex conjugate, because I want to have a real Lagrangian. If I have a representation that is complex, I also have the complex conjugate. But in a more general case where I map I to j, I'm completely fine defining theories based only on Ri. So the second case would be that Rj is not part of the model. And so the physical consequences of these 2 options are, I mean, people pointed out to me there's actually a third logical possibility, since there are mathematicians around. And another logical possibility is that Ri is not part of the model either. Okay, so but then I would start with a different discussion. Anyway, so physical consequences, and it's exactly analogous to in the case of the complex conjugation, where you map operators to the complex conjugate. Now, in this case, you just map operators to other operators, okay, because they contain representations. The representation would be mapped to other representations. So you can always view this as a permutation of operators. And the only possible effect of such a permutation of operators is that it actually can be equivalently described as a transformation of the couplings. So if I have an action which has some fields, I map the fields by the automorphism, I can always write this as I can always roll this over to the couplings, okay, and view the same theory but with modified couplings. And now this automorphism, by definition, it's not a symmetry, because if it would be a symmetry, I would include it in my symmetry and then again discuss the question of automorphisms based on that symmetry. But you find, I mean, see, it would be a symmetry if the couplings fulfill some, equation. So the couplings are the same as this transform couplings, then this would be a symmetry. So having an automorphism in some sense looks like an explicitly broken symmetry. Okay, and this is for the case that I, both Ri and Rj are included in the model, and I can actually have this permutation of operators. In the second case, where I have Ri but not Rj, the transformation is not possible. I try to map something on some other thing which is not in my theory. Okay, so what it happens is I'm not mapping the theory to itself, but I map the theory to a different theory. And I would call this kind of a dual theory. And since this transformation is definitely not a symmetry of my theory, this is called explicitly and maximally broken transformation. And just to give you an example for both of these possibilities, and again I go back to the standard model. The example for the first case would be the CP transformation of the standard model, where I map representations to complex conjugates for all of them. And and I can wonder whether it's a symmetry or not. I have to look at my couplings. Is it a symmetry? No, because the couplings don't fulfill this relation. So this transformation is broken explicitly by the couplings, by the values of the couplings of my theory. In the second case would be, say, for example, the parity transformation of the standard model, where I map my theory. I use an automorphism to map representations to other representations, but they are not in the theory. They are not there. I cannot do this mapping on the theory. I end up with a different theory. This transformation is explicitly and maximally broken. Even though I use here CP and P again as examples, note that this is much more general than C or P. Yeah, it's just for RI and RJ. Okay. So let me give you an explicit example, which is the 3 Higgs doublet model with the delta 54 symmetry. By the way, this is and this is why we discussed this model in detail in the first place. It's a kind of historic model where people found by explicit computation in 83 that you know, this model it's phenomenologically close to viable model. I mean, it's just extension of the Higgs sector of the standard model. They've computed vacuum expectation values for these Higgses and found there are phases which are rigid and fixed. Somehow they didn't understand it, but they call it geometrical T violation. And so this was a puzzle until you find all this overhead with the automorphisms and why, you know, I will shortly show you how they fix these phases. So the model is, you have 3 Higgs doublet models. So I call these the Higgses. So these Higgses are, you know, like in the standard model. So they are fields which transform in the same way as the standard model Higgs. So it's singlet under strong interactions, but it's a doublet under electroweak. And I take 3 copies of this guy to transform in a triplet of delta 54. Now note, this is a situation. I have delta 54 with of type 1, but I don't have any of these doublets around. Okay, so I'm perfectly fine defining CP transformations here for this field. It's not a situation which is rigid enough to cause CP violation immediately by the complex Clebsch-Gordon coefficients, because there are no doublets at all.
Does the delta 54 come from something? Does it come from something, or is it put in by hand?
Oh, it's put in by hand, but I mean, what would it come from? I mean, where do symmetries come from?
Well, yeah, there's all kinds of things that you could imagine, but okay. So the answer is that it's put in by hand. That's okay. And okay, and just to confirm, so this is, so if you take the standard model and you were to augment it by these 3 Higgs, so is this still experimentally okay?
And this depends on the exact point in parameter space. I mean, you have to make these Higgses somewhat decoupled from the rest of the standard model. So either you make them heavy or you make them what is called aligned. But since we haven't seen them at the LHC, there is some bounds on the parameter space, but it's not entirely excluded. And it would be very hard to entirely exclude any of these Higgs modifications, because you can always make these guys heavy. I mean, at least, I mean, so you will find a standard model Higgs somewhere in here. And if you give this guy light enough mass and the other guy's heavy enough mass, I mean, there may be involved, maybe some fine tuning involved, but you can always take a decoupling limit in these models.
Okay, thanks.
So the way how people usually think of this, if they write down the Higgs potential, so they take all delta 54 invariant terms, all independent, and write it down in what I would call the human basis. So you think of, you know, these terms, like you say, okay, what term is invariant? Let's take H1 dagger H1, H2 dagger H2, and you say H1 dagger H2, H2 dagger H1, and so on. And so you go through and you make this list of easy operators, and you define the potential. But I argue that this is not the smartest way to do it, because you have the symmetry, and the symmetry has an automorphism. And so the way how I prefer to write this potential is a different way. It's exactly the same potential. It's just reparameterized, just rewritten. I take linear combinations of the invariant and according linear combination of the couplings and rewrite it in such a way that I have 5. I mean, it's just the same number of degrees of freedom, but I have my mass term here, and I have 5 real degrees of freedom, which is A couplings, which are over the reals. And I have some more complicated invariants, which are not so nice to spell out. This is why I hide them here. But you will see that the structure of the potential in writing in this, what I call the automorphism basis, is superior in many ways. So if you minimize this potential, this problem is just such that you can still do it by hand, or say like say analytically. you can find the minima of this potential. So what you have to do in order to do that, usually this is how you do it. If you do it the first time, is you have to solve. I mean, of course, you take derivatives of these guys set into 0, and then go through all the pain of solving a coupled system of 12 coupled cubic equations. And you find the stationary points, and you find that there are 4 classes of them, which are given. I mean, the directions here are the direction in the space of delta 54 and the 6 triplet spaces 1, 1, 1, omega 1, 1, and so on. Where omega is a complex phase, and this is also the complex phase that these guys found back in '83. And this is, I mean, you find, I mean, omega is the rigid phase. It's a physical phase between the vacuum expectation values of these Higgses. So you can find all this by you know, hardcore explicit computations. But you can also realize that, of course, this model has the symmetry, which has a large automorphism group, namely the permutation of 4 objects. And so they act on the Higgs. I mean, 12 of these S4 transformation act as on the triplet as complex conjugations, and other 12 act as you know, linear transformation. And we consider all of these transformation, all 24 of them. And what happens is, if I, you know, transform this Higgs triplet under automorphisms, I find how it acts, this transformation acts on the potential and acts on the stationary points. And in the way I've written, you may already guess what happens is it acts as permutation, all 24 possible permutations of these invariants, and all 24 possible permutations of these VEFs. Okay, so this action is much more complicated if I write the potential in what I call a human basis. So this 3 example model is an example for some very general statements on automorphism. Okay, so if I have, I mean, if I start here, I think my parameter space of the theory, if I want to say make a scan and kind of answer the question that Cohl asked, it's like what part of the parameter space is still allowed, what can physically happen in different corners of the parameter space. I would have to think, if I want to scan this, I would have to scan each of these A's over all the reals. But after realizing I have this large automorphism transformation at my disposal, I find that the physical parameter space is actually reduced from taking A1 to A4 over all the reals to one wedge in this space. You know, I can always use this automorphism to order my couplings without loss of generality, such that I can always take them, say, in a hierarchical way. And I'm guaranteed to not miss any physics by doing that. So I immediately can reduce the size of the parameter space by a factor of 4 factorial here, 24, or whatever the size of my automorphism group is. Also, since the stationary points, and this is true not only for the minima, it's also true for saddle points and other stationary points. That, I mean, this is, we just know by explicit computation. We don't have a theorem on that, but we know if you find a stationary point, that the stationary points transform in representations of the automorphisms. So, for example, here I have 4 different categories of possible vacuum expectation values, and these form a 4-blet of these automorphism groups. This is very nice, okay, because if I know, you know, for example, I could guess a VEF and just use all the automorphisms to find all the others. This would be the most stupid strategy here to find. I mean, see, for example, this 111 guy is super easy to find, and then I find all his 24 friends. And actually, I find even more because I can also still use the inner automorphisms. Anyway, so in this case, I mean, a more general statement is that the stationary points here, or the VEFs, are calculable from a homogeneous linear equation. Okay, I don't have to solve this complicated system of 12 coupled cubic equations. The solutions are given by linear equation, homogeneous linear equation. And this, of course, makes my life much simpler to compute the stationary points. And it also once you understand how this matrix M comes about, you understand how this fixes the relative phases between the vacuum expectation values. And you understand the origin of this geometrical T variation. Another statement is, maybe it's a bit of a trivial statement, but I think it's important because it may have important physical applications that we have not explored at all, is that these automorphisms can give rise to emergent symmetries. What do I mean by that? So imagine I have the potential has a minimum at one of these stationary points. Imagine it sits, the theory kind of low temperature sits in one of these points. I have automorphisms, since it's all possible permutation of these vacuum expectation values. There will be a subset S3 of these guys, which leave each VEF invariant. Okay. There's not being permuted with the other guys. This means the VEF, and this is not, I mean, it's I can have a symmetry of the vacuum expectation value. And by definition, I mean, by how I found it, this is not a symmetry of the potential because it's an automorphism. It has a non-trivial action on the potential, but it doesn't, I mean, it acts trivial on the VEF. So this means the VEF has a higher symmetry than the potential. This is what I would call emergent symmetries, the opposite of spontaneous symmetry breaking. And then what I also argued before is that CP and symmetry enhancement in the theory is very transparent in this what I call out eigenbases. So if I use the parametrization given to me by the symmetries of the model, and I use that, I stick to that, I find very easy expressions. For example, for the Yarl's-Cook invariant, the CP odd invariant of this model, it's given simply by the differences of each of all these A's. And whereas if I write this in the basis, the human basis with the lambdas and so on, and this would be more longer than a page. You know, it's just a mess. This is the basis you want to use if you discuss this model. Okay, so it has also important implications at the quantum level. So if I go on and I compute the RG running, I find the beta functions for my couplings A, and I find it's enough to compute the beta function for one of these A's because all the other beta functions are just given by all possible permutations of these A's, and they will give me, you know, in a short way to say this, also the beta functions form representations of the group of automorphisms. This means the beta functions come in multiplet as the couplings come in multiplet, as the invariants come in multiplets. All of these objects will come in multiplets of the group of automorphisms. And it's not hard to see because, as I told you, you may think of these automorphisms to some extent as explicitly broken symmetries. And so you find immediately that at points in the parameter space where you would conserve this automorphism, where you would add it to the symmetries of your theory, that you would not escape from such a point by RG running. This is a symmetry enhanced point. And so coming from the other way, you say, I have this theory, it has delta 54 symmetry, and I wonder about the running the RG fixed points of in the space of couplings. I find that the hyperplanes in the space of couplings, which are give the boundaries of the RGE flow, they're immediately found by knowing about the automorphisms. And sorry, this is a pretty bad plot because this is still work in progress. But what I want to show here is, I mean, it's really bad to see here. But the point is, this gives you RGE running in projection of some space, say A1, A2. And what should we be able to see here, it's not really clear, is that you actually run exactly in this cone. I mean, the couplings would run down here and then take a sharp edge and go out. And they will never ever cross these hyperplanes. So in this way, I argue that the automorphisms also determine the boundaries and fixed points of the RGE flow. I'm not saying all of the boundaries and all of the fixed points are given by these automorphisms. It's a much stronger statement. I'm just saying if I know about the outs, I definitely will find all of the corresponding fixed points and boundaries. There could be more. Okay, this is actually all that I have to say. Let me see how good in time. Yeah. So as a summary, these automorphisms are symmetries of symmetries and vice versa. Understanding them is crucial in the standard model and BSM to understand CP transformations and CP violation. And you can carry this on to T and others. There are type 1 groups for which CP violating phases can be predicted from a symmetry principle because these groups are ones which don't like complex conjugation. And then try to convince you that these automorphisms are more general than CP transformations. And knowing them gives you profound insights about permutation of invariants, simple shortcuts to computation of stationary points, possibility of emergent symmetries, and RGE flow and RGE fixed points, just to name the stuff that we already know about. There might be more. So if you believe in the importance of symmetries in physics, why not consider the symmetries of symmetries? They are also important. An obvious target for this exploration is, at least how I started with this and how I will continue with that, is to try to understand, make sense of this flavor puzzle using this stuff, because it's exactly of this kind. You know, we have copies of stuff which transforms weird and we don't understand how. And for example, I mean, this again goes, takes an example from string theory, is in string theory, there's this what is called an Arine lattice formulation of string theory, where you basically think of the compactified space-time. It kind of has some crystal structure in position and momentum space. And in this case, it's really interesting because the automorphisms of these crystals tell you, I mean, they unify in these situations the flavor symmetry, what is called modular transformations, including T-duality of string theory and the CP transformation. And you find that all of these different transformations, including the flavor symmetry, are part of the automorphisms of this Narayan lattice. So the general exploration of this, guys, has just started. Would be very interesting to know the automorphism of more complicated groups. You know, for this finite, simple and small groups, you can all do this by hand. But for you know, there's very sparse discussion literature on using this systematically. For example, Poincaré or conformal group or whatever group you can think of. So far, I've only shown you discrete automorphisms. The question is, can there be continuous automorphisms? And there are some statements in the literature that scaling can be thought of as an automorphism. And this would be the only example I know of a continuous automorphism, continuous outer automorphism. Then this may be related to group extension problem. I haven't talked about that, but it's you learn about these groups by learning about the outer automorphisms. And important question is, what is the relation of automorphisms and gauge symmetries? Especially because having automorphisms, they have certain redundancies, which I haven't talked about much. But it seems like, at least for some cases that Cohl has discussed earlier, it seems that there is a relation with the quaternions and or even octonions and their redundancies, like their automorphism are somewhere related to gauge symmetries. And so on. I mean, there can be it's related to maybe to S dualities of string theory and possibly any form of duality, but this has to be explored on a case-by-case basis. Okay, that's all what I wanted to say. Thank you.
Thank you for such a wonderful talk, Andreas. I really enjoyed that. So does any brave soul have a question? Oh, we've got a couple of hands up. All right, so Andreas, I'm going to unmute you here.
Yeah. Thank you. So I would like to ask probably that is there a way to, or is it known already, what is the complete list of the outer automorphism of the standard model Lie algebra?
I would think so. Yes. I mean, if you just mean the Gage and Lawrence group,
yes,
I would say yes. Yes, we know all of them.
Mm-hmm. So these you can derive from the linking diagrams of them, or
yes. I mean, there are two steps, right? I mean, you need to know it on the algebra, which you get from the linking diagram. Then you need to know it acting on the representations, which you have to solve the consistency condition for. Mm-hmm. But both of these steps have been done in general for U1 and for SUN, and so this in general, and then specifically for the Lawrence group, these steps have been done. So I would argue that we know all of them.
Mm-hmm. Okay, and the second one is a remark. So you asked in your last slide that you don't know an example of a continuous outer automorphism. So well, in a toy models, one can create such. So for example, we had a recent construction published in JHAB that, for example, you can construct a gauge theory like toy model, which has its structure group is the complexified Heisenberg group, semi-direct product with the SLC2, so with the Lorentz group. And in that case, the SLC2 component will be the outer automorphism of, so to speak, of the Heisenberg group. So it is possible to construct such.
It is a very pleasing statement to me. I really have to look at this paper. This is very interesting.
Let's change it. Okay.
I mean, I always expected there must be cool examples, and this sounds like a very cool example to exactly this statement.
Okay. Okay, so there's no hands up. All right. So can I ask about this, about your comment here right at the end, relations about automorphisms and gauge symmetries relating to quaternions and octonions? Are you referring to triality perhaps, or?
Yeah, I guess you know this much better than I do, but what I tried to find these statements in your papers, but I couldn't. But I also didn't spend too much time trying. But so wasn't there a statement that in some of your constructions you find actually the gauge symmetry of the standard model as automorphism group of these division algebras?
As outer, no. As the outer automorphism groups of the division algebras, no. So with respect to outer automorphisms, so people often talk about triality, and most often they talk about triality of the octonions, but also there is triality of quaternions and all the division algebras as well. But the first reference I'm aware of is, there might be earlier ones, is Pierre Ramon suggesting octonionic triality to explain the existence of 3 generations. And there have been many people since then that have made that same observation.
Yeah, which is obviously a very tempting observation, and it's also closely related to this triality in SO8, I think.
Yes, exactly. That's exactly the same one. That's right. And to add to that, one of my collaborators, Mia Hughes, showed recently, if you look at quaternionic triality, that it's possible to write down a Higgs system, Yukawa Higgs system, where the Higgs has a left-right symmetry, And anyway, she showed that you can write down a Yukawa term which has quaternionic triality. It's a really nice result.
I have to look at that too. Is that paper out?
It's with a journal right now, so it's it's not out, but there's a
On the archive? Oh.
we haven't put it on the archive yet, but we have it up on Persa. So there was an Octonions conference at Perimeter Institute, and we gave a talk on it, so it's available on Persa. I think the title of our talk might have been Division Algebraic Symmetry Breaking. And it was Mia's section was the one where she talked about this quaternionic triality. So does anybody else have any more questions? Well, that was a fantastic talk. I really enjoyed it. I'm just gonna.
Thanks.
My pleasure. At any rate, so thank you so much for giving us such a wonderful talk, and thank you to Andreas for his questions, and thank you so much for I really love the material in this talk. This was fantastic. So for in the next couple of weeks, our next speaker is Jorge Zanelli from CECS in Chile, and he is going to be telling us about unconventional supersymmetry. So that's in 2 weeks' time. So thank you again so much, Andreas, for a wonderful talk, and I hope to see everybody again in the next 2 weeks.
Thank you.